Hi class, welcome to our next and last section for chapter 5. This is 5.5. This is Indeterminate Forms and L'Hopital's rule. So we're kind of bringing it all the way back, almost all the way back, right? So we start off with reviewing functions, basically reviewing algebra, trig, pre-cal, that kind of stuff for chapter 1. Chapter 2 was when we started to talk about limits and the different ways of finding limits and things like that. So we're going all the way back to limits, basically, okay? So we're going to use all the stuff that we know now, right, to be able to find limits that previously we were not able to find or calculate before. So up until this point, I don't even think I've shown you or presented to you a limit yet that we weren't able to actually find or calculate, but we do have some that we can't find, and so now we're going to talk about how to find those. So, L'Hopital rule is a method for computing limits, again, that we were previously unable to compute. Previously, if we did have something that was in an indeterminate form, we would use a numerical method. Okay, we actually did see, I guess we did see one that was, no, it wasn't in an indeterminate form, but we did use a numerical method for calculating a limit a few times in the videos. For those in my class, you've done more than a few of them through your homework and your practice and your classwork problems and things like that. But in this video series, we've only done one or two numerical methods for looking at limits, right? So approaching from the left side and the right side and making sure that as the average rate of change got smaller and smaller and smaller, that the left side and the right side agreed to the same number, right? That's kind of what we did before. So that's the numerical method. It's not very fun. It's very tedious. It takes a long time. It's much easier to be able to calculate a limit. It's much nicer when our limits are continuous at the point that we're trying to evaluate at. That's always nice. So what we're going to be looking at now is when we have pretty much the worst limits possible, right? So how do we evaluate those? So things like when I have a ratio function, a quotient of functions, where both of those independently go to 0 as I approach my value a. Now this can be infinity, negative infinity, 7, it doesn't matter, right? Just any value a here. So as I approach a, the numerator and denominator go to 0. So previously what we were doing was, if this was the case, we were kind of looking at it and saying, well, or infinity over infinity, okay? And we were saying, well, which one dominates? Which one goes faster, right? So for instance, we were really just focused on a polynomial over a polynomial. Well, which one goes to infinity faster? Well, that's the one that wins, right? If the one on the bottom goes faster, then my whole limit goes to 0. If the one in the numerator goes to infinity faster, then the whole limit goes to infinity, right? We can do that again with polynomials over exponential functions. Exponential functions grow way faster than polynomials. So if I have a ratio of a polynomial over an exponential, the exponential is always going to win, okay? And that's nice to know conceptually, but there's also going to be times where it's not helpful. Even that doesn't help us, right? That's more so when we're looking at things for large values of a, when a goes to infinity. But what about when we're approaching an asymptote, right? So a being an asymptote, then how does that work, right? How does that differ for us? So that's when we use L'Hopital's rule. Okay. So L'Hopital, he was a French mathematician, if you can't tell by his name. And so his method for approaching difficult limits was to take their derivatives. Okay, so here we need f and g to be differentiable. We need the derivative of g, our bottom function here, to not be 0 on my interval that contains a. Okay, so it needs to be continuous. The derivative needs to be continuous on that interval. At the point of a, it could be not continuous, and that's fine. Okay, so let's say that the limit as I go to a of my function f goes to 0, and the limit of g also goes to 0 as x approaches a. Or let's say that f goes to plus or minus infinity, and g also goes to plus or minus infinity as x goes to a. Then the limit of f of x over g of x is the same as the limit of the ratio of their derivatives. Okay. Now, why is this helpful? Because it's possible that my functions go to 0 or infinity, but their derivatives do not. Okay, so oftentimes I can take their derivative, and this will help the limits. So the process is, there's a couple of different methods, right? But the method we're going to focus on, the most useful method for right now, we'll talk about other times when we have to change it up a little bit. But for right now, we're just going to be trying to take the derivative of the numerator and the denominator. When we use L'Hopital's rule, we use this notation, right? So if you've noticed, as we go through and we do our limits, I always keep limit of this as we go through. I never not write the limit form because we're taking a limit. So it can be confusing to the reader if your function looks like one thing and then all of a sudden it's completely different, and algebraically it doesn't look like what happened should have happened, because you're taking derivatives, not canceling something out, for instance, right? So we always use an h over the equal sign when we're using L'Hopital's rule, so that we signify to the reader we are taking derivatives of both of these functions. Okay. So there's several indeterminate forms. 0 over 0 or infinity over infinity are not the only indeterminate forms. There are other indeterminate forms as well. So since we have other indeterminate forms besides 0 over 0 or infinity over infinity, what happens is that when we encounter an indeterminate form that's not 0 over 0 or infinity over infinity, we need to algebraically manipulate the thing we're taking the limit of, our function, so that it looks like 0 over 0 or infinity over infinity. Okay, it's very, very important. This is an integral step for using L'Hopital's rule when it's not very apparent that that's what we should do. Okay, so if it seems like it's pretty much impossible for us to take our limit, or it's just difficult, period, we probably need to manipulate it into a ratio of functions, into a quotient function, so that we can use L'Hopital's rule on it, right? So there are, again, a few indeterminate forms. One of those forms are called indeterminate products. It's basically when, instead of having a ratio of functions, you have something times something, and one of those functions goes to 0 and the other goes to infinity. And it's not very clear which one dominates, right? Now you might be saying, well, yeah, if I multiply 0 times infinity, then that's 0 no matter what. But not if the other function grows faster than the other one decreases, right? So if I'm multiplying two functions and one gets very large much faster than the other one goes to 0, then for very large values, the larger function is the one that dominates, okay? So this is indeterminate of the form 0 times infinity. So depending on, if it's clear which one grows faster, then you can just say, oh, it goes to 0 or it goes to infinity. But if it's not clear which one goes faster, we have to manipulate this algebraically so it turns into a quotient of functions, so then we can use L'Hopital's rule. Okay, so that's kind of the idea. Is if it doesn't look like a quotient of functions and it's indeterminate form, we make it a quotient of functions so that we can take those derivatives. Okay, so one of the ways that we would do that is we just multiply by 1 over the reciprocal. Okay, so that's the same thing as f times g. So if I take this and I simplify it, I will get out f times g. So really you just pick one of your functions and you divide it by the other function. You divide its reciprocal by that function. Okay, so it depends on which one. Your choice really doesn't matter. It kind of matters. It matters in that one of the forms might be harder than the other. Okay, maybe this is harder to calculate than this is when we do L'Hopital's rule. So then maybe I'd want to use this form for me when I do my derivatives. It really just depends on your functions that you have. Okay, so once I take my product of functions and then I turn them into a division, a quotient of functions, then it should be in the form 0 over 0 or infinity over infinity, and then I can use L'Hopital's rule. Okay. We also have indeterminate differences. This is, again, when one function goes to 0 and another goes to infinity, okay, or possibly they both go to infinity, and you don't know which one goes to infinity first, right? If f of x grows faster than g, then my limit would be infinity, right? If g goes to infinity faster than f does, my limit would be negative infinity, okay? Or what if they go at the same time, at the same rate, and then I actually get out 0? So we have indeterminate differences as well, right? So f grows faster, then my limit is infinity. If g grows faster, it's negative infinity. If they grow at the same rate, it's going to be some finite value or possibly 0. So when it looks like this, my goal again is to try to manipulate it into a form so that it is a quotient of functions. Maybe I can't manipulate it to be a quotient, but possibly I can manipulate it into by adding them and subtracting them together. Maybe these two functions will simplify when they're being added or subtracted. Okay, or I'm sorry, when they're being subtracted together. Okay, so again, we try to convert it into a quotient by using a common denominator, or by rationalization, or factoring out a common factor so that we have an indeterminate form. So that's one of the three approaches that we have when we have a difference. Okay, so depending on what this looks like, maybe these are both rational functions, so we add them together so that they have a common denominator, so it turns into something like these two. Or perhaps we have to pull out a common factor, or maybe there's radicals going on and we have to rationalize. Okay, or maybe you make up a factor to pull out. That could happen too. Okay. Next is indeterminate powers. So when we have something to a power, right? So I have two functions. One of those functions is in the power position, and let's say they both go to 0. Well, which one dominates, right? 0 is just 0, okay? But what's 0 to the 0 power? Is that 1? I don't know, right? Because anything to the 0 power is 1. But if it's 0 to the 0 power, that can't be 1. So that's an indeterminate type as well. And it's a power, right? We have a function and another function, so this one doesn't make sense. Let's say it's infinity and 0. So the base goes to infinity, but the power goes to 0. So do I go to infinity or do I go to 1, right? Which one dominates? Most of the time it's not very clear which one, so we have to use L'Hopital's rule, right? Or let's say that I have a base of 1 to a power of infinity or negative infinity. Well, you would say, well, yeah, it should just go to 1, because 1 times 1 times 1 forever is always 1. But my function isn't 1. It goes to 1, okay? And this function goes to infinity. So does that mean it's getting very, very large, right? So this one is indeterminate as well. When you have indeterminate powers, it's almost impossible to get it into a rational form. So when we have it in a power form, we have to be a little bit tricky, okay? There's two methods for doing this. One is to use logarithmic differentiation, right? Which is, I'm glad we covered it, because generally in a calculus class, I actually skipped through logarithmic differentiation, so I'm glad we covered that. We would do this logarithmically. So we would set our function f of x to the g of x equal to y, okay? And then we would take natural log of both sides. So I'll say y equals my function. I take natural log of both sides, which means that this power function comes down into a multiplier position, and then I can take the limit of both sides. So throughout the entire process, I'm being equal, right? I'm taking natural log of both sides, I'm taking the limit of both sides, etc., right? I can also do this by, instead of taking natural log of both sides, I can raise each side to the power of e, okay? Sorry, rather than taking e to both sides, we would just manipulate this into an exponential form, right? So I'm taking e to the natural log of this function, because we know e and natural log cancels out to be f of x to g of the x. And then the power rule of natural log makes me bring the g of x down here in this exponent position, okay? So sometimes it's easier to look at it like this, and then I would take the limit of this to whatever value, okay? So both are useful. They both have their appropriate times and places. Can you get away with doing one all the time? Probably. I believe I tend to use one more often than two, because we have a whole method of differentiating that's almost identical to this, so that's the one that we'll be kind of playing with as we go. So let's go ahead and do some examples. Okay, so again, if it's already indeterminate form of 0 over 0 or infinity over infinity, just take the derivative of the top and bottom. Okay, if we have one of these other indeterminate forms, okay, products for instance, these are rather easy. You just kind of manipulate this multiplication so it looks like a fraction. For the differences, you got to be a little bit craftier here. Either rationalize, pull out a factor. If it's like a quotient minus another quotient, then you try to combine them or pull out a common factor. One of those two should help you out. Indeterminate powers, we got to use either method 1, which we should be semi-comfortable with, or you can try to approach it using method 2 here, which is similar. Instead of taking natural log of both of these things, you're just going to write it, you're just going to raise this to the power of e. You're going to take natural log of this thing and raise it to e. That way the e and the natural log cancel out, and so you're not really changing the value of your function, you're just manipulating it so you can look at it as an exponential function. Okay, so let's do an example. We're going to find the following limits. The first one is the limit as theta goes to 0 of sine of theta over theta. So we looked at this towards the beginning, except we had sine of theta over the absolute value of theta. But this is a common one. Okay, this is a very important limit. It comes up very, very often. It's very, very difficult to calculate. As it is right now, there's no method to figure out what it is, because if you plug in 0, you get 0 over 0, which is an indeterminate form. So up until now, the only way that we had to try to calculate this thing was by plugging in values of theta very, very close to 0 as we approach from the left, right, from the negative side, and as we approach from the right, from the positive side. So a numerical method. Here, we can, both of these functions are continuous at 0, okay, or over an interval containing 0. So we can just differentiate both. So this turns into the limit of cosine of theta over 1, so just cosine theta, right? So again, previously we had to do this numerically. Now we can use L'Hopital's rule. So this is the same, right? This is the notation saying I'm using L'Hopital's rule, because if I didn't use this and I just said, hey, this equals to that, you'd be like, how are these two things equal? How is sine over theta? How is sine of theta over theta equal to cosine theta over 1? There's no way that those two things are the same. You're telling the reader you're using L'Hopital's rule. So then they're like, oh, I'm using derivatives here because I'm using L'Hopital's rule. So it's you being nice to the reader so that they can understand the process that's going on. So here, we just need to take the limit as cosine of theta goes to 0, which is continuous at this point. So I just plug in 0 and I get out 1. Okay, so L'Hopital's rule makes this much, much easier to calculate. Here we have the limit as x goes to infinity of this function. Now this is very difficult because look what happens. What happens? Well, x goes to infinity. Sine of pi over x goes to something else. It doesn't go to infinity, right? It's like me plugging in values of sine, where I'm plugging in very, very small values. So I'm plugging in values as I get closer and closer to 0. Okay, and we know that sine of 0 is 0, right? So when I'm plugging in values of 0 into sine, I get 0. So, right, this was 0 over 0, which is indeterminate form. Here, I'm getting infinity times 0, basically. So x gets large, right? Doesn't it get large faster than sine goes to 0? Like, I don't know, because I'm plugging in very large values of infinity. Because this is a sine function, it oscillates, right? I can't tell, okay? You can't tell which one grows faster. So this goes to infinity. This is equivalent to saying sine of 0, which is 0. So I'm indeterminate of the form infinity times 0. Okay, I don't know which one grows faster. It's possible that this goes to a constant, that it doesn't even go to 0 or infinity, right? Like this one. This was 0 over 0. It went to 1. Okay, so the numerator didn't dominate, the denominator didn't dominate, and it's not like they went at the same rate either. Okay, because this goes to 0 at a different rate than this does, because they're different types of functions. Okay, so here we've got to use our form. There's two different ways to do this. I can divide sine by 1 over x, or I can divide x by 1 over sine of pi over x, right? It doesn't matter which one we choose. One might be easier than the other. Generally, we want to look at which one is going to be easier for when I take derivatives. Okay, so for this function, I can rewrite it as x over 1 divided by sine pi over x, or I can rewrite this as sine pi over x divided by 1 over x. So which one looks like it'll be easier when I take derivatives? Okay, well, derivative of x is 1. This is going to be cosecant of pi over x. I have no idea what the derivative of cosecant is. I'm going to have to go back and look at some values, or I'm going to have to use the quotient rule. Probably going to have to use the quotient rule because using the quotient rule will allow me to use the chain rule here. So either I go back and look at the formula for derivative of cosecant and use the chain rule, or I can just take the derivative of sine, and I know that this one is natural log. To me, this second one looks like it's a lot easier, a lot quicker. I know these off the top of my head. I don't have to go back and reference anything. So I'll just do this. So again, remember, I'm not doing the quotient rule. Taking the derivative of the numerator, and I'm taking the derivative of the denominator separately. Okay, that's what L'Hopital's rule is. It is not me taking the derivative of the entire thing. Okay, common mistake. So again, let's go back to rule real fast. I take the derivative of the numerator and the derivative of the denominator. It is not the quotient rule because I'm using L'Hopital's rule, not the quotient rule. Alright, so let's come back to our example. Okay, so again, the second option to me looks a lot easier, so that's the derivative that I'm going to use. So I have my limit of x times sine pi over x as x goes to infinity. I'm going to manipulate it so it's the exact same value. I'm not changing it in value. I'm just changing the way it looks so it's indeterminate of the form that I want. This I know goes to 0. This bottom one I know goes to 0 as well. So that's nice. Here, this first form that I had, the numerator went to infinity and this one went to infinity. So same, it's still an indeterminate form. I'm going to use L'Hopital's rule. Okay. 1 over x, I'm sorry, it doesn't go to natural log. It goes to it's x to the negative 1 power. So it goes to negative x to negative 2. And then here sine goes to cosine. The inside function has a derivative of negative pi x to the negative 2. Okay. So from here, if you notice, I actually get to cancel something out. So that's always nice. So this turns into pi times cosine pi over x. Take the limit as x goes to infinity. Well, this is basically like me plugging in cosine of 0, which is 1. So this thing goes to pi. Now, I bet you had no idea that something that was indeterminate form of infinity times 0 was going to go to pi. I'm sure you thought it was going to go to 0 or infinity. So again, these things can go to constant values. So we got to make sure that we are using L'Hopital's rule as we go through these. Okay, you can't just say, oh, I think this one's going to go faster than this, so it's going to go to 0, or this goes faster than that, so it's going to go to infinity. You got to use the rules. Okay, here we have another rule or another problem, right? We have the limit as x goes to infinity of x minus natural log of x. So if you notice, I'm kind of going through one at a time. A, we had just a regular indeterminate form, 0 over 0. B was a indeterminate product. Now I have an indeterminate difference. Okay, so I have to try to do something to get this to be indeterminate form. Okay, so there's no common denominator for me to use to try to add them together. There's no rationals, right? There's no radicals, so I can't rationalize anything, or and so I really don't know what to do, right? I think the easiest thing to do will probably be to make up something to factor out. Okay, so just to make sure it's indeterminate form, x goes to infinity when I plug in large values. Natural log goes to infinity when I plug in large values. So then it turns into, well, which one grows faster? Well, we know x grows faster, but does that mean that it goes to infinity? We can't say, right? We just saw from the last example, you can't just say, oh, this one goes faster, so this is what's going to happen. So I'm an indeterminate form of a difference, an indeterminate difference. So what we're going to do is we're going to pull out a common factor. Okay, So what I'm going to do is I'm going to pull out x. I'm going to pull out an x, so I will have x times, this will be 1, and this will be natural log over x. I'm pulling out a common factor of x. Why? Just to see what happens. Okay, so I need something to happen. So let's go ahead and pull out x. This now goes into infinity. Natural log over x, natural log of x over x. This is now infinity over infinity. Okay, which I don't know what happens to this thing, which one grows faster or what the limit is. But I can combine this now in this form, right? So I have x times x minus natural log of x over x, which was the same thing as I had before, right? It's kind of like I just took my previous answer and wrote it as x over x, and look at the inside, right? X minus natural log is the same as I had before. I just have an x on the outside. I just multiply the whole thing times x over x, basically. Okay, that helps you out also to think about it that way. So I'm gonna use my properties of limits, and I'm gonna separate these into two different things. I'm taking the limit of x and the limit of x minus natural log of x over x. So I know from my properties of limits I can distribute this limit. This one goes into infinity. This one I can't tell you for certain exactly what it does, right? So we're going to use L'Hopital's rule, not on the x, but on this one, okay? So we're going to have 1 over x over 1. Let's go ahead and simplify this. So this turns into 1 minus 1 over x. Okay. So as I go to infinity, this one will go to 0, and this will go to 1, and this will go to infinity, which means the entire thing goes to infinity. Okay. So here I factored out a function and I kept it normal as I used L'Hopital's rule on one of my functions, since it was in indeterminate form. Because x is not indeterminate form, but this is. Okay, this one is. Alright, let's do one more. So you should be able to tell that this is an indeterminate power because I have a function to another function. This function, e to the negative x goes to 0, x goes to infinity as I take the limit for very large values of x. So this is an indeterminate form of infinity to the 0 power. Alright, so we have two different methods to approach this. I'm going to just go with the one. So I'm going to say this thing is equal to y. Take the natural log of both sides, okay, which allows me to take this power function, e to the negative x, and drop it down as a multiplier. Okay. So now I can take the limit of both sides, the natural log of y as x goes to infinity, and the limit of e to the negative x times the natural log of x as e goes to infinity. Right. So if I'm looking at this, this is what this looks like. It's indeterminate form, right? It's infinity over infinity, which is nice because I need it in this form. So then I can use L'Hopital's rule. This turns into 1 over x over e to the x. So now I have 0 over infinity. So both things pretty much go to 0. I could simplify this a little bit more, but it's not going to be super helpful. Okay, so 1 over x e to the x. So the whole thing on the bottom goes to 0. So this goes to 0. So the limit of natural log of y goes to 0. And that is going to be my answer, right? So the limit of this is the same as the limit of y as x goes to infinity. So there we go. Sometimes, by the way, I don't have any examples here where this happens, but there's times where you have to use L'Hopital's possibly more than one time, sometimes 2 to 3 times. So you would use L'Hopital's rule, simplify, then maybe you get somewhere where you're not really ready to say what the limit is, and then you use L'Hopital's one more time.